Okay, let's dive right into this explainer. Today, we're unpacking a foundational chapter in physics by tackling a mystery that literally stumped humanity for millennia. I mean, what actually governs motion? Now, we all know the basic math of velocity and acceleration, but today, we're going a lot deeper. We're going to explore the fundamental laws of motion and completely reframe exactly why things move the way they do. So picture this. A skater gliding smoothly across a fresh sheet of ice, or a kid pushing a toy car across the living room floor. What is actually required to keep them moving? Does motion always demand a push? Well, that is the central question we're answering today. Here's our quick roadmap. We'll look at the mystery of motion, Aristotle's big mistake, and force, mass, and momentum. Then we'll hit conservation of momentum, balance and common forces, and wrap up by solving mechanics problems. Let's kick things off with Section 1, the mystery of motion. Our everyday, common sense experiences are constantly tricking us. Think about it. To move a resting football, someone has to physically kick it. To throw a stone up, you gotta give it a push. A moving toy car, it eventually rolls to a dead stop if you don't keep pushing it. Left entirely to themselves, it really seems like all bodies just naturally come to rest. Because of this, it is incredibly intuitive to believe that an external agency is always needed to sustain motion. But as we'll see, human intuition isn't always the sharpest physicist in the room. And that brings us right to Section 2, which features the massive plot twist of this whole chapter, Aristotle's big mistake. It's totally fascinating to contrast two giant historical viewpoints here. The great Greek thinker Aristotle looked at the world and concluded that an external force is required to keep a body in motion. I mean, it feels right, doesn't it? But it's actually entirely wrong. It is wild that it took 2,000 years for Galileo to come along and realize the truth. By imagining a perfectly smooth, frictionless plane, Galileo uncovered a paradigm-shifting reality. Objects move with constant velocity if no net force acts on them. They don't naturally want to stop. So the absolutely crucial point here is that Galileo identified an invisible culprit, friction. A moving toy car doesn't stop because its motion just naturally decays. It stops because the invisible external force of friction with the floor is physically opposing it. When a kid pushes a toy car at a steady speed, they actually aren't creating motion at all. They are just perfectly canceling out the friction. True uniform motion means the net external force is exactly zero. Galileo essentially imagined a world stripped of these opposing forces, and that led directly to the true law of inertia. With the mystery of inertia solved, let's jump into Section 3, force, mass, and momentum. This is where Isaac Newton formalizes Galileo's brilliant insights. To really wrap our heads around force, we first have to understand momentum. Momentum is the product of an object's mass and its velocity. Think of it as the true currency of motion. Seriously, think about it. It takes a massively greater opposing force to stop a heavy, fully loaded semi-truck than a tiny little compact car, even if they are traveling at the exact same speed down the highway. Why? Because the truck just has significantly more momentum. And this brilliantly illustrates exactly how Newton built his laws. The first law simply describes a world with zero net external force, meaning absolutely no acceleration, just constant velocity. That's our old friend Galileo's inertia. But Newton's second law kicks in the very moment that net force is no longer zero. It tells us that force equals the rate of change of momentum. If mass is fixed, you get the legendary equation F equals ma. It seamlessly takes over right where the first law leaves off. It's beautiful. But hey, what about sudden impacts, like a baseball bouncing hard off a brick wall? In these explosive cases, a very large force acts for a very, very short duration. It's frankly almost impossible to measure the exact force and the exact tiny fraction of a second separately. So instead, we measure their product, which we call impulse. Impulse is the force multiplied by the time duration, and it perfectly equals the total, measurable change in the object's momentum. Moving right along to Section 4. Let's see how all this builds into an incredible rule for the universe, the conservation of momentum. Now, before we talk conservation, we've got to bring up Newton's third law. You've definitely heard the phrase, for every action there is an equal and opposite reaction. In physics terms, this simply means forces always occur in pairs. If body A exerts a force on body B exerts an exact equal and opposite force back on body A. This simple, unavoidable fact is the glue that allows us to apply our laws to complex systems of interacting objects. Let's apply this to a classic, everyday physics example, firing a gun.
When fired, the bullet experiences a forward force for a split second, gaining forward momentum. By the third law we just talked about, the gun experiences the exact same force backward for the exact same amount of time, gaining backward momentum. And that backward momentum, that's the recoil you feel in your shoulder. Take a second to picture the math here. If you add the positive momentum of the bullet and the negative momentum of the gun, they perfectly cancel each other out. Because they started at rest with zero momentum, the total final momentum of this isolated system remains exactly zero. The momentum was perfectly conserved. It's like magic, but it's just math.
Having established those universal rules, let's step into Section 5 to ground them in reality by looking at balance and common forces. Out in the real world of mechanics, we constantly encounter a few very common forces. Gravity is the pervasive one, right? Pulling things down from a distance. But almost everything else we deal with is a contact force. Think of a heavy block supported by the tension in a rope, a compressed spring pushing back against your hand, or just the normal force of a desk holding up your laptop. These are all grounded, everyday interactions dictating how things move or don't move. When an object is perfectly still or moving perfectly steadily, it is in equilibrium. This strictly requires zero net external force. All those tensions, gravities, and normal forces we just mentioned, they have to perfectly cancel each other out. If you actually draw the vector arrows for all the forces acting on a suspended particle, they will form a perfectly closed polygon. To solve for them, we just ensure that all the horizontal forces add up to zero, and all the vertical forces add up to zero. Which brings us to our final section, solving mechanics problems. Let's talk about how to turn these concepts into a practical toolkit. The absolute secret weapon for conquering any mechanics problem is the free body diagram. You don't try to look at the whole messy world all at once. First, you mentally isolate one specific part of an assembly. That becomes your system. Second, you identify the environment, meaning every single external force acting on your system from the outside. Third, you draw a super simple diagram showing just your object and those specific force vectors. By stripping away all the visual noise, the path to the solution becomes incredibly clear. It's a real game changer. I want to leave you with a real mind bender of an application. Imagine a stone is dropped from a train that is accelerating forward at 1 meter per second squared. What is the stone's horizontal acceleration the exact moment it leaves the window? Now, ignoring air resistance, the answer is exactly 0. No way, right? But the moment it loses contact with the train, that horizontal force vanishes. Acceleration only exists while a force is actively being applied. The stone carries absolutely no memory of its acceleration from a millisecond ago. Now, if that doesn't completely change how you view every moving object around you, honestly, what will? Keep observing the forces around you, and I'll catch you in the next explainer.